Every month we see Microsoft shipping patches for Windows and other things. We see Oracle shipping patches quarterly. And it's quite clear that we haven't solved the software security problem yet, despite all the advances in technology and knowledge that's been going on in the industry for several years. So we're trying to... This is a talk on basically how we can solve this really difficult problem, yeah? Every developer will tell you the first rule of programming is there's always one more bug, which in theory means how can you ever make sure that's not going to be a security bug, which means you'll be getting your software exploited, which is probably bad. So software's getting more complex, bigger programs. The current version of Windows is about 50 million lines, I believe, whereas the one 20 years ago that I first looked at was about 60 million. So, in 20 years, Windows has tripled in size. And the larger software gets, the more complex it gets. You can't possibly figure out all the interactions. So this is a kind of talk about how we might try and make that problem a little more tractable. Hopefully there'll be a few good war stories. Anyone's got any questions, just shout. And the names have been changed to protect the guilty, I should say. So basic content, who, what, where, when, why, how, and questions. So who does this? I think it's important to think about the sort of people who are actually working in the industry trying to make products like Windows and other things more secure. In my experience, people come from a variety of backgrounds. We've got government, academia, consultancy, system administration, antivirus, and there are plenty of others. One of the best guys I ever knew in this industry studied classical Chinese at university. So there's no kind of right way to get into it. People come from all sorts of backgrounds. You need certain skills to do the job. Primarily, if you're trying to secure products, you need to be a decent programmer. You need a background in the languages, you need to know all of the common coding errors, you need to understand security, you need to understand all the different types of vulnerabilities there are, how they might be exploited. You need to understand things like network protocols, file formats. There's a huge amount of skills. The interesting thing about these skills is they're all stuff that's not actually that difficult to learn. They're all things that are well documented. If you want to know what a JPEG looks like, you can go and read the spec for a JPEG. What you can't teach people is personality traits, and I think this is equally important. The example I always give is it's far easier to teach someone to be able to play the piano than it is to make them a good musician. To be good at this job, you need to have certain traits. So things like you have to question absolutely everything. Don't take any assumption for granted. As I'll show you later, some people make the worst possible assumptions. And it's really kind of obvious to a security person that they're not right, but anyway. You need to have that kind of... Well, one of the reasons I think hackers get this kind of underground image is because they generally don't respect authority. So when a developer tells you my product is really secure or my product is unbreakable, your natural instinct is, oh yeah, pull the other one. And I think, when Oracle did the Unbreakable campaign, that was the worst possible thing they could do, because within a couple of weeks, David Litchfield had found 120 bugs. So you have to have that kind of mindset. You have to think like an attacker. It's really important. A really good analogy I find is, imagine where you live, there's a whole bunch of break-ins. So the advice from the police is you should be putting locks on your windows. So you go down to B&Q and you find that everyone else has been there buying the locks, and there aren't quite enough locks left for your windows. Now from a defender's perspective, putting locks on half the windows in your house makes it more secure. From an attacker's perspective, you just find the window without the lock. So I think that's a really important way to think. You have to think like an attacker. That's the only way you'll actually break this stuff. And you also need things like passion and curiosity. Again, you have to care fundamentally, I think. So what do we do? First part of this stuff is you really need to educate people. There's no good whinging about people making mistakes if you've never told them what they should or shouldn't do. So in this industry you find, we do presentations, we do training courses, we speak at conferences, all these kind of things. So you make people aware of the mistakes they're going to make before they make them. So we've got more of a a right to whinge after they make them, I suppose. We do consultancy. We sit down with people, we hold their hand, we give them guidance, we give them detailed technical support. We tell them how they should be doing their job better, because we're security experts and by and large they're not. We do assessment. This is the majority of the product security job is actually looking at products that are coming out and figuring out whether they're any good or not. And we do research. The field of security has been evolving ever since I've been in it for the last 20 years. There are new bugs, there are new types of attack to become aware of. From a commercial point of view, IRACTIV does a lot of research into sort of areas that no one's really looked at, because that generates business. Similarly, when you do some business, that often sparks up a whole bunch of ideas to research. So these two feed off each other, and that keeps the job interesting for a lot of people. Why do we do it? Fundamentally, developers are human. They make mistakes. They're under increased pressure to deliver stuff faster, quicker, cheaper, and security is probably not uppermost in their minds when their boss is kind of on their back, moaning about features and prettiness and all these things. Which leads us to the first rule of programming: there's always one more bug. And that's kind of been universal as long as there have been computers, and I'm sure it still will be. But not all bugs are equal. At the outside, you've got quality bugs. So that's where you can make a program do something that is not expected. Within that, you have reliability bugs. That's where you can make a program do stuff which it doesn't handle, so normally it will just crash. And as a subset of that, you've got security bugs, which are bugs where you can actually control what the program does. Now, these are strict subsets. It should be obvious that if you fix all the quality bugs, you fix all the security bugs. So when I get a 2-page email from a developer explaining why they're not going to fix a bug because they don't really think it's a provable security bug, and it's a one-line code change, I get really annoyed. And people do that all the time, because in companies like Microsoft and other big software vendors, developers are basically rated at the end of the year on how many bugs in their code were fixed. Not how many bugs were found, but how many were fixed. So the more bugs that they have to fix, the lower their bonus is going to be. That's why they hate fixing bugs. In Microsoft and other places, they have this kind of dev test culture where developers get rated on how many bugs they have to fix. Testers get rated on how many bugs they find that do get fixed, which obviously produces a little bit of a conflict, shall we say. Resources. For every one person at Microsoft or BlackBerry or Amazon or whatever who's trying to secure the code, you've probably got thousands trying to break it. Attackers outnumber defenders massively by several orders of magnitude, not just in terms of the number of people, but in terms of the amount of time they can spend. You know, I have some friends who work for Microsoft, and we were discussing the other night that for things like Pwn to Own, the annual competition in CanSec West, you get various companies putting several hundred people on it for a year to find effectively one exploitable chain from an email up to the kernel. You know, Microsoft don't have the resources to put 300 people looking for effectively 2 or 3 bugs for a year. So everything's in the attacker's favour. Time, people, resources, and from the inside, from the kind of defender perspective, you have to kind of work out how you can best address this balance. Okay, the clicky thing. Do you have the power lead for the clicky thing? Try it again.
I'll try now. That's the question.
I guess there really was one more bug.
This is just one dead battery, so
No, it's not that.
okay. So, when to get involved? Basically, the later you leave fixing a bug in the process, the more it costs to fix it. So fixing something at the earliest possible stage, so preventing a bug ever getting into the code base, is by far the most economical way of fixing it. When Microsoft ship a patch, it costs them a huge amount of money, just because of the amount of testing. They have to make sure it's not going to break anything. If Windows Update breaks Oracle, Microsoft gets sued. That's the bottom line. So how do we do this? There's basically a kind of three-pronged attack, which sums up the way product security is actually done in practice. First thing is prevention. You want to stop as many bugs getting into the code base as possible. It's far cheaper, it's far better for developers and for security people that bugs never make it into the code base than they do, but then you have to find them and get them fixed and so on. Again, two ways that happens. One is by education, by telling developers about all the mistakes, by making them aware of all the mistakes they're going to make before they make them. And then there's enforcement. Now that's things like you're turning on compiler warnings and making them errors so that people can't make common programming errors. Compilers are actually incredibly good at spotting security bugs. The problem is some of the things they spot, developers don't know will be security bugs, they disable the warnings, because then maybe they're not security bugs all the time, just some of the time. Okay? So we might also do things like deprecate certain APIs which we know are sufficiently difficult to use safely that the safest thing to do is just not use them at all. So things like the Stracopies of this world, which back in the late 90s, early 2000s were responsible for stacks of really nasty bugs. So we can actually make changes to the environment which prevents bugs ever getting into the code base. There's also detection. So, okay, we'll stop a load of bugs getting in, but guaranteed some people will still write buggy code. So how are we going to find them? Well, finding them all manually is going to be really tricky, so we're going to try and automate some of the analysis. The static analysis. Now this is where you look at the code in its entirety and try and use it to find bugs. Now, static analysis is very, very good. There are certain commercial tools like Clockwork and Coverity which find a whole bunch of bugs really reliably. Unfortunately, they have lots of false positives. This is an artifact static analysis in that it has a very high false positive rate traditionally. A really good static analysis tool has probably 80% false positives. So only 1 in 5 bugs is actually a bug. The flip side to that is, well, that's an artifact of the way these tools work, in that if you think about the way a program runs, you have various points where you'll have a branch and then it will come back together again. Every time that happens, you lose accuracy because you don't know which path the code actually followed. So the way most of these tools work is they kind of either make a guess or assume it followed kind of both paths at the same time, and that's why you lose accuracy and that's why you get lots of false positives. You can do something called path-sensitive analysis, which is incredibly accurate. It doesn't suffer from false positives. Unfortunately, it's incredibly expensive computationally in the sense of the number of paths tends to go exponentially with the size of the code. So before long, you'll find it's just not feasible to actually do the analysis on any reasonable size program. Then there's dynamic analysis. In the security world, that's mostly what we call fuzz testing, which is where you take well-formed input and then you manipulate it in some way to change parts of the input file and run the program and see what happened. And if it crashed, that's great, we found a bug. And if it doesn't crash, we might try a different mutation. Now this has been refined quite a lot over the last few years. There's programs like AFL, American Fuzzy Lock, which is a great fuzzer. And what that does is it measures the code coverage of each test case. And every time a mutation causes the program to use a bit of code it hasn't run before, it remembers that and says, right, that's worth keeping. If a test case doesn't exercise any new code, it decides, actually, we don't really need to worry about that and we can throw it away. And by that kind of approach and actually measuring code coverage, it's been incredibly effective at finding large numbers of bugs in a reasonable amount of time. The big problem with fuzzing is you never know that you found everything. There have been examples of various bugs in things like image parsers, where there was a JPEG parser that Microsoft had, which had been fuzzed hundreds of millions of times, hundreds of millions of test cases, but there was a particular bug in it that only manifested itself when there was a very unusual field in the JPEG file, and it turns out that in practice almost no JPEGs ever have this in practice, but yeah, because someone had actually taken the code apart and worked out that there was this obscure code path that had never been tested, they found a really nasty bug. Same thing happened with Word. MSRC got a case in of a document saying run this. That document could not be created in Microsoft Word. It contained records that had been taken out of Word years ago and replaced with new versions. But someone had read the spec and actually constructed stuff by hand, which is not trivial for Word. It's a horrible spec. Again, so testing is always only going to ever be a partial thing. What most people do is they'll run lots of fuzzing, and when they stop finding new bugs and stop exercising new code, they'll give up. And again, that's only ever going to be a partial fix, because you'll never really have assurance that you found all the bugs. Because as a software tester, you know, when I do a pen test as a consultant, people are always wondering, how many bugs did you find? That's the wrong question. You don't care how many bugs someone found, you care how many are left. You've got to think about these things the right way. You know, I could find 20 bugs in a game, I could find 200 bugs, I could find none. That doesn't tell you anything about the security of the product. Because what you care about is how many are left. You know, that's the thing with Windows, that's why we get monthly patches. Microsoft have run lots of code, lots of testing on all of their code, but it's the number of bugs that are left that matter. But the thing is, if you can find stuff automatically, it's actually possible to fix it automatically. So here's an example that I did when I was at Microsoft, where you have the first line of code here is an uninitialized pointer. If, in this case, if P gets used before it's actually initialized, then that's potentially an interesting bug. So the correct way to do it is initialize it to null. And it turns out you can pretty much do that with a regex at the bottom there. And yes, we fixed about 3,500 of these bugs, just automatically. And it turned out doing that actually found a couple of other bugs because code was relying on the fact the pointer was uninitialized. Or at least they were relying on the fact the pointer was non-null. So, yeah. But the interesting thing is this won't break anything that's not already broken. It's a provably good fix. So, again, this sort of stuff you can automate. Just do it. You know, don't worry if there is actually an uninitialized pointer bug here. Just do it anyway. You know, it's far easier to do that automatically than it is to kind of go through each one and work out whether you really need to. So that's automated analysis. The flip side, and where most people spend a lot of their time, is in manual analysis. So code review. I've done a lot of code review in my time, and these are the numbers of lines a day that a reasonable code reviewer can do. They're not very high. Bear in mind, most programs are hundreds of thousands, if not millions of lines long. So being able to do 1,500 lines of C a day, if the thing you're looking at is 100,000 lines of C, okay, 60 odd days work, the chance of someone actually paying you to do 60-day code review, fairly small. What I'm trying to get at is most programs are infeasibly large to manually review every line. So what we do is we adopt a time-limit approach, in that we try and work out which bits of the code we really need to review, and the kind of various ways we do that. First, and I think the most important thing is to understand developers. Developers, as I mentioned, are not stupid, they just don't know as much about security as security specialists. They're under lots of pressure to deliver lots of really good stuff in very tight time frames. So figure out, where are they going to cut the corners? Where are they going to kind of miss things out? What assumptions are they going to make that might not be the most sensible ones? So one thing to do is make sure you're aware of all the common coding errors. If you just Google for top 10 C coding errors or Java coding errors, there's loads. You know, the CERT Secure Coding Standard has got lots and lots of really good information on these. So figure out what mistakes are they going to make and just go and look for those mistakes. Most of them you can do with fairly simple string searching. What assumptions are they going to make? I genuinely have seen this code, or at least the binary that contain this code. Basically, no one's going to have a password bigger than 128 characters, right? So we're just going to allow 128 characters. And that was in a real password manager. Yeah. But it's a reasonable assumption from the perspective of, yeah, no one really does have a password longer than 128 characters. But it's a completely bad assumption in the sense of security. Because that was basically a local system for the locking prompt on every Windows box in a particular organization. Compromises. Developers will make compromises. As a security professional, I'd like to think security was top of my priority list. If you're a developer working for, say, a graphics card manufacturer, speed is probably your top concern. If you're working for an embedded device manufacturer, code size might be your concern, or battery life. So, well, I say you should add all these checks to make sure your input's valid. Developers might rightly say, well, that will slow down my code, or make it larger so I can't fit it in the EEPROM anymore. Or if you tell me I should use HTTPS rather than HTTP to connect to my server, that's going to shorten the battery life by a factor of 3. These are genuinely valid concerns. Security doesn't always win. So when you look at various embedded devices particularly, you'll find they use unencrypted HTTP simply to make the battery life bigger, because doing an SSL negotiation is computationally very expensive. Security features. We would always look at security features purely on the grounds that any bugs are likely to be very significant, very high impact. So if your authentication can be bypassed, that's probably very bad. If your encryption doesn't work properly, that's also very bad, and so on. Because you're actually making security statements about your product, and in the world of GDPR and other things, if they're not as good as you think, that's probably not great. Code quality, something else we look a lot at. So this is where we might run a whole bunch of automated scans across the code to measure quality. Now, I know quality is a very nebulous term, but we do try and look for a couple of specific things. So coding style is interesting. If you see code written like this, you probably want to go and slap the developer. If anyone can tell me what that does, I'll be massively impressed.
There's a space, remove the space.
So what this does is, well, I'll tell, if anyone wants to know, come and find me afterwards and I'll tell you. It's not what you'd expect. On a slightly more serious note, one thing we look at is compiler warnings. Not necessarily errors, we just compile the code with the warnings turned up to 11. And we just record where the warnings were in the code. And then that's just kind of like a visualization of which paths contain the most warnings. And what that will do is it'll say, well, actually, a lot of the warnings are in this bit of the code base, so maybe that's the one you want to review, because the code is, in some sense, of lower quality. Similarly, we can do the same for unsafe APIs. So if you look for string copy or whatever, or stuff you know is indicative of insecure programming practice. Again, you just look for it in the code, record where the paths of where you find it, and then visualize it and go and have a look in those particular areas. That's quite a nice, easy one. Something else we'd always look at is attack surface. So this is where somebody can actually introduce data into your program. So this might be network, it might be files, it might be interprocess communication. And we try and get a list of all the places where an attacker can actually introduce data, because that will tell us how this program is fundamentally going to be attacked. And that process can be somewhat automated. Then what we probably try and do is data flow analysis. So we try and take that attack surface and follow the data downwards through the program to see how it gets used, either until it was validated to the point where we thought it was going to be safe, or until we found an interesting use of it. And again, this is where it gets really kind of tedious, frankly, because it involves just looking through pages and pages and pages of code for days on end. And that's kind of where you just have to sit down and read the code. And there's no rocket science, there's no secret sauce that code reviewers know that the rest of the world doesn't. You sit down and you read through the code looking for mistakes. And after you've done it for several years, you'll kind of get an instinct for where code smells bad, or where you see something that kind of doesn't look quite right, but you won't be sure why. And you'll probably be a little bit faster about identifying dead ends more quickly. But there is no magic to code review. I used to teach a course in reverse engineering, and people always think that experienced reverse engineers knew something they didn't. And the only thing we knew that they didn't is just how hard it was. And they, you know, when they say this is going to take hours, you go, yeah, actually it's probably going to be taking days rather than hours. But yeah, there was no magic, there was no hidden knowledge. It's not like learning a magic trick, you just know it's as difficult as you think. It's like if you want to become a concert pianist, there's no magic, you just practice for 8 hours a day for 20 years. That's kind of all there is to it. And you have a good teacher and so on, but fundamentally, you can have the best teacher in the world. If you don't put the practice on the piano, you won't be able to play the piano. And it's the same with this stuff. You just have to do it and spend hours and hours doing it.
Did it stop again? Yeah. Yeah. Absolutely. Turned it out because it's not here yet.
Okay, so we've prevented some bugs getting into the code base. We've tried to detect some of the ones that have. What we know from experience, we're not going to find everything. So the last line of defense is mitigations. Now, mitigations tend to actually cover two distinct things. One is what I would call mitigations, the other one is defense in depth. So security mitigations fundamentally reduce the likelihood of a compromise. So what they tend to do is turn security bugs into reliability bugs. So the idea is that you can still send a program invalid input and you can still crash it, but you can't control what it does, which is a reliability bug, not a security bug. So this is things like stack cookies, ASLR, depth, heap hardening, pool hardening, all of these kind of things that lots of manufacturers have been putting in their code recently. And again, they reduce the likelihood of a compromise. There's also defense in depth. Now this is a kind of partner. This reduces the severity of a compromise. So even if someone does get code execution on your box, they'll find the process is running as a low privilege user in a sandbox. Or they'll find it doesn't have access to anything because it's running under a unique user ID that has no permissions anywhere else. Or it's things like fine-grained access control on files or any other objects. Or it's principle of least privilege or fewer root processes, all those kind of things. So that's defense in depth, where you reduce the severity of the compromise by effectively reducing the privilege of the code that has been compromised. So, in conclusion, there is always one more bug, but hopefully, with a bit of luck and a bit of hard work, you can make software somewhat secure for some value of secure. Anyone have any questions? Yeah.
Are there any good guides on where to focus on?
Where to focus on?
Yeah.
Not really. I mean, well, if you read things like the CERT secure coding guidelines, they'll tell you how to write secure code. There are lots of books you can buy on secure coding. There are very few on code review. I think the expectation is if you know how to write secure code, then you can spot code that's not secure, which isn't always the case. I mean, one one argument I've had with people is that Trojanizing source code is a lot easier than people think, because all of the practices we have are designed to spot unintentional mistakes rather than deliberately trying to do the wrong thing. So that's another interesting avenue to explore at some point, I think. But yeah, I've never read a good book on how to do code review. I'm sure there might be some, but yeah, most of the books are secure coding. Yeah.
Does any of your review focus on, rather than finding sort of crash-type coding errors, but on finding the program doing something perfectly correctly, but not what was intended originally?
So that sort of thing would be caught by, I guess, functional testing, or by regression testing maybe. I think security people do write some tests for software. Most test teams have got security specialists in them, but that's a very difficult one, because if you think about, say, a file parser for, I don't know, JPEGs, writing a program that exercises the entire JPEG spec, malforming every combination of every possible field, is probably unfeasible computationally.
I was thinking more about business application type logic
Oh,
errors.
okay, yeah. So for logic errors, yeah, I mean,
As you approach it.
yeah, most people would work out what a program ought to do. So, for example, can you put a negative amount of money in for the cost of something, that kind of thing. So there would normally be some ways of doing these things where there would be very obvious things you could try. So if you've got numerical input, you try floating point, integers, negatives, exponentials, but then you'd also try strings, you'd also try non-ASCII characters, you try a whole bunch of stuff. That's fine for those sort of simple things. Once you get to more complicated binary file formats, it's a lot more difficult.
So for an organisation who wants